Welcome to the Thinking Abyss podcast, a philosophical journey through consciousness, reality, and the phenomena that challenge our understanding of existence. From ancient wisdom to cutting-edge theories, we explore where philosophy meets science and curiosity leads to the edge of the unknown.
Welcome to the deep dive. Today, we're tackling something, well, huge. We're looking at quantum mechanics.
Right. The most successful scientific theory we've ever come up with, arguably.
Exactly. It underpins, pretty much all modern technology. Your phone, lasers, computers.
Everything electronic, basically. The precision is just astounding. We can predict particle behavior incredibly accurately.
And this is the core of our dive today, when you actually try to understand what the theory says about reality.
It gets weird, really weird. It seems to break our fundamental ideas about existence, about cause and effect, even about what it means to observe something.
That's the conflict, isn't it? This incredible practical success versus this conceptual chaos.
It forces you to confront these deep questions.
Yeah.
What does it mean for something to be somewhere? Can things be in multiple places at once?
And can measuring something actually change what's real? That's the kind of territory we're in.
It sounds philosophical, but it comes directly from the physics, from the experiments.
So our mission today is to unpack why. Why does this super precise theory lead to such, mind-bending puzzles? How do we square the solid, predictable world we see around us?
The chair you're sitting on.
Right, with this fuzzy, probabilistic quantum world underneath.
And for you listening, the big question to keep in mind is, if observation is key, what does existence even mean when no one's looking?
Let's start by rewinding a bit, back to a time when physics felt, more comfortable.
Yes, the classical world. It's important to remember how neat and tidy it all seemed, especially after Newton.
It really was. The universe is a giant clockwork machine, right?
Yeah.
Everything running according to precise laws.
Absolutely. Determinism was key.
Yeah.
If you knew the position and momentum of every particle.
Which you couldn't, obviously, but in principle.
In principle, yes, you could calculate the entire past and future of the universe. No surprises, no randomness.
And everything had definite properties. A ball has a location, a speed, whether you look or not.
Exactly. Objective reality. Things are what they are, independent of us. Tiny, solid particles obeying clear, local rules.
And the scientist, just a bystander, taking notes.
Passive observation. Measurement just revealed what was already there. It didn't change anything.
Such a clean picture, elegant, deterministic.
Until the cracks started showing. And they didn't come from philosophers questioning reality. They came from physicists hitting problems they couldn't solve with the old rules.
It started with explaining, of all things, why hot objects glow the way they do. Black body radiation.
Right. Max Planck, 1900. The existing physics just couldn't predict the spectrum of light emitted. The math broke down.
So what did he do?
He made a sort of desperate move, mathematically. He proposed that energy couldn't be emitted or absorbed smoothly, continuously. It had to come in discrete packets, little chunks. He called them quanta.
So not like a smooth flow of water, but like firing tiny pellets of energy.
Exactly. It introduced a graininess to energy that wasn't there before. He didn't even fully believe the implications at first, I think.
Just a mathematical trick to make the equations work?
Initially, maybe. But then, just 5 years later, Einstein took that idea of quanta seriously.
Einstein. He wasn't just about relativity then.
No, his work on the photoelectric effect won him the Nobel Prize, actually. He used Planck's quantum idea to explain why shining light on metal kicks out electrons.
How did quanta help there?
He showed that light itself, which everyone knew as a wave, had to be acting like a stream of particles, photons, in this interaction. Each photon packet carried a quantum of energy.
So now light is both a wave and a particle. That sounds contradictory.
It was. And that was the real turning point. People like Bohr, Heisenberg, Schrödinger, they realized these weren't just small fixes to classical physics.
It was a whole new game.
A completely new framework, one that fundamentally challenged objectivity and determinism.
Which leads us to the main interpretation, the one most physicists learn first, Copenhagen.
The Copenhagen interpretation, yeah. Developed mainly by Niels Bohr and Werner Heisenberg in the 1920s. It became the standard way of thinking about this new quantum world.
And what's the core idea, the really radical part?
It's superposition. Before you measure a quantum particle, it doesn't have a definite property like position or spin. It exists in a kind of haze of all possibilities at once.
A haze.
Mathematically, it's described by something called the wave function, which represents all the potential outcomes and their probabilities simultaneously. The particle simply isn't in a definite state.
Until?
Until you measure it. The act of measurement forces the wave function to, well, collapse. It snaps out of that haze of possibilities into one single definite reality.
So the observer isn't passive anymore. Looking makes reality happen, in a sense.
That's the implication. Observation plays an active, crucial role in determining what is. It turns potential into actual.
And the outcome of that collapse, is it predictable?
No. That's the other key point. It's fundamentally probabilistic, random. You can calculate the odds of getting spin up versus spin down, for instance, but you can never know for sure which one it will be beforehand.
And that's what Einstein hated, right? The God does not play dice comment.
Precisely. He couldn't accept this inherent randomness. He felt the theory must be incomplete. There had to be some underlying hidden variables that, if we knew them, would restore determinism and make everything predictable again.
Did they find those hidden variables?
Now, that's a story we'll get to. But the standard theory, Copenhagen, worked perfectly for predicting experiments, even with its conceptual weirdness.
So we have this incredibly successful theory that seems to describe a reality that's fundamentally fuzzy, probabilistic, and observer-dependent.
And that tension generated some famous paradoxes, thought experiments, designed to push this weirdness to its limits. They really help us grasp the core strangeness.
Okay, let's dive into those. Where should we start? The cat.
Schrodinger's cat, yes, it's probably the most famous one, proposed by Erwin Schrödinger himself in 1935.
And he didn't actually want people to think there could be a half-dead, half-alive cat, right?
Exactly. He meant it as a reductio ad absurdum. He was trying to show how ridiculous it seemed to apply the quantum rules of superposition, which seems okay for tiny atoms, to a large-scale everyday object like a cat.
Okay, remind us of the setup. It's a bit morbid.
It is. Imagine a sealed box. Inside you have a cat. You also have a tiny amount of radioactive material, just one atom, let's say. This atom has exactly a 50% chance of decaying in the next hour. If it does decay, it triggers a Geiger counter.
Okay.
The Geiger counter is hooked up to a hammer, which will smash a vial of poison gas if triggered.
And if the atom doesn't decay?
Then nothing happens. The Geiger counter stays silent, the hammer doesn't fall, the poison isn't released, and the cat remains happily alive.
Right. Classically, after an hour, the cat is either definitively dead or definitively alive. Simple.
But now apply the quantum rules. That single radioactive atom, before we check on it, is governed by quantum mechanics.
So it's in a superposition.
Yes. According to the math, it's simultaneously in a state of decayed and not decayed. Both possibilities exist together in the wave function.
Okay, the atom is fuzzy, but the cat.
Here's the crucial link. The cat's fate is directly mechanically tied to the quantum state of that atom. If the atom is decayed and not decayed,
then the cat must be dead and alive simultaneously.
According to a strict application of the quantum formalism, yes. The entire system, atom, Geiger counter, hammer, poison, cat, is described by one combined wave function that includes both possibilities coexisting.
Until
an observer opens the box and performs a measurement. At that moment, the wave function for the whole system collapses, and reality snaps into just one state. Either the atom decayed and the cat is dead, or the atom didn't decay and the cat is alive.
That's the absurdity Schrödinger wanted to highlight. We know cats aren't both dead and alive. So where does the quantum description break down? When does the fuzziness stop and the definite reality we experience take over?
That's the heart of the measurement problem, which we'll come back to. But there's a modern understanding that helps resolve the practical absurdity of the cat, even if it doesn't solve the deep philosophical issue. It's called decoherence.
Decoherence, right. What does that mean practically?
It means that quantum superposition is incredibly fragile. A quantum system can only maintain that delicate state of multiple possibilities if it's perfectly isolated from its environment.
And a cat in a box is definitely not isolated.
Not even close. It's a large, warm, complex system, constantly interacting with everything around it, air molecules bumping into it, heat radiating the box walls.
So the environment is constantly sort of measuring it, nudging it.
That's a good way to put it. These countless tiny interactions with the environment cause the quantum information, the both-at-onceness, to leak out and dissipate incredibly rapidly. The superposition effectively gets scrambled and lost to the environment.
So decoherence explains why we don't see macroscopic superpositions like dead and alive cats. The interaction with the environment destroys the quantum weirdness very quickly.
Essentially, yes.
Yeah.
It doesn't necessarily cause the collapse into one state, but it makes the different possibilities unable to interfere with each other, mimicking collapse for all practical purposes. It explains the transition from the quantum microworld to the classical macro world we experience.
But physicists are actually trying to create these cat states now, aren't they? With bigger and bigger things.
They are. Pushing the boundaries, trying to see how large an object can be put into superposition before decoherence inevitably takes over. They've done it with large molecules, tiny vibrating membranes. It's a race to probe that quantum classical divide. The cat isn't just a thought experiment anymore. It's an experimental goal.
Okay, so superposition is weird. Decoherence makes it hard to see in big things. What about the wave-particle thing? That seems just as fundamental.
Wave-particle duality, yes. And the best illustration is the classic double-slit experiment.
This one involves firing things. Electrons.
Right.
Photons.
Either works. Let's say electrons. You fire them one at a time towards a barrier with two narrow parallel slits cut into it. Behind the barrier is a detector screen that records where each electron hits.
Okay. If electrons are like tiny balls, you'd expect them to go through one slit or the other, and you'd see two bright bands on the screen right behind the slits.
That's the classical expectation. Two distinct clumps of hits.
But that's not what happens.
Not at all. When you run the experiment and build up the pattern from many individual electron hits, you don't get two bands. You get an interference pattern.
Interference.
That's
Like waves.
Exactly like waves. Alternating bright and dark stripes across the screen. This is the classic signature of waves passing through both slits simultaneously and interfering with themselves. Crests meeting crests make bright spots. Crests meeting troughs cancel out to make dark spots.
But you fired them one at a time. How can a single electron interfere with itself? It has to go through both slits at once.
That's what the wave behavior suggests. As it approaches the slits, the electron isn't a particle at a specific point. It's a wave function, a wave of probability that spreads out and passes through both slits.
Okay, mind-bending. But then comes the really weird part, right? What happens if you try to watch which slit the electron goes through?
Ah, yes. The observer effect strikes again. If you place a detector right at the slits, any kind of device that can tell you, okay, this electron went through the left slit or that one went through the right slit.
What happens to the pattern?
The interference pattern completely disappears, vanishes.
Gone. What do you see instead?
You see exactly what the classical picture predicted. Two distinct bands. Right behind the slits, the electrons suddenly behave like well-behaved little particles, going through one slit or the other, but not both.
So just looking at which path it takes forces it to choose a path. It stops being a wave and becomes a particle.
Precisely. The very act of acquiring which path information destroys the wave-like superposition state that allowed for interference. It's as if the electron's nature fundamentally changes depending on the question you ask it experimentally.
Ask it a wave question. Where will it land after potentially interfering? It acts like a wave. Ask it a particle question. Which slit did it use? It acts like a particle.
That's the essence of wave-particle duality. Quantum objects aren't really waves or particles in our classical sense. Their manifestation depends entirely on the experimental context, on what you're measuring. Our classical categories just don't fit.
And this isn't just electrons, you said.
No, they've done double-slit experiments with photons, atoms, even complex molecules like buckyball C60 molecules. The wave nature persists for surprisingly large things as long as you don't measure which path they take.
It really undermines the idea that things have fixed inherent properties. Their properties seem to emerge from how we interact with them.
Which leads us directly to the core problem underlying all of this, the measurement problem.
Okay, the measurement problem. This feels like the central mystery we keep bumping up against.
It really is. It's the conceptual black hole at the heart of quantum mechanics. We've said systems exist in superposition until measured, and then the wave function collapses.
Right.
But the standard quantum theory, the Schrödinger equation that describes how wave functions evolve, absolutely does not include any mechanism for this collapse.
Yeah.
It just describes smooth, continuous evolution of the superposition.
So the theory tells you how the fuzziness evolves, but not how it suddenly becomes sharp and definite.
Exactly. There's a gap. How does the measurement do that? When exactly does the collapse happen? What physically constitutes a measurement?
Does it need a conscious person? Does a Geiger counter clicking count? A camera recording it?
That's the huge ambiguity. If measurement is just a physical interaction, then the measuring device itself should be part of the quantum system.
Uh-oh. So if the Geiger counter measures the radioactive atom...
The Geiger counter, being made of atoms obeying quantum rules, should itself enter a superposition of having clicked and not having clicked, entangled with the atom state.
So now the counter is fuzzy.
Right. And then if a camera records the counter, the camera should enter a superposition of recorded click and recorded no click.
And then my eye looking at the camera, my brain processing it. Where does it start?
That's the infinite regress problem, sometimes called the von Neumann chain. If everything obeys quantum mechanics, the superposition should just keep expanding outwards, entangling more and more of the universe, including the observer. Where does the buck stop? Where does reality become definite?
It seems like measurement isn't just passively observing reality, but actively creating it somehow.
That's the unavoidable conclusion from the formalism, challenging that classical idea of an objective world existing independently of observation.
And this problem, this lack of a collapse mechanism in the core theory, is why people came up with all those different interpretations we need to talk about later.
Precisely. Copenhagen sort of papers over it. Many worlds eliminates it. Hidden variables tries to hide it. Consciousness-based ideas pinpoint the observer. They're all attempts to solve or dissolve the measurement problem. It's a fundamental sticking point.
Okay. One more major paradox before we get to the interpretations. The one that Einstein found particularly disturbing. Entanglement.
Entanglement. Spooky action at a distance, as Einstein famously called it.
What is entanglement, basically?
It's a quantum connection between two or more particles. You can set them up so they share the same unified quantum state, no matter how far apart they get.
Shared state. How?
Imagine creating two particles, say, electrons from a process where their total spin must be zero. If one spins up, the other must spin down to conserve that zero total spin. Quantum mechanics allows them to be created in a superposition state where neither has a definite spin, but they're perfectly anti-correlated.
So before measurement, electron A is spin up ND spin down, and electron B is also spin up ND spin down, but they're linked.
Exactly. They're linked in a single wave function. A is up, ADB is down. Or A is down, ADB is up. Now you separate these two electrons, send one to the moon, keep the other here.
Okay.
Now you measure the spin of the electron here on Earth. Let's say you find it's spinning up.
What about the one on the moon?
Instantly. Yeah, I mean, instantly. Faster than light could travel that distance, for absolute certain that if someone on the moon measures that electron spin, they will find it spinning down.
Instant knowledge across vast distance. That sounds like it violates relativity, the cosmic speed limit.
It looks like it. This is what bothered Einstein so much. It violates the principle of locality, the idea that an object can only be influenced by its immediate surroundings, and any influence has to travel through space, limited by the speed of light. Entanglement seems to bypass space entirely.
So this led to another famous paper, the EPR paradox.
Yes, Einstein, Podolsky, and Rosen wrote a paper in 1935 arguing that this spooky action proved quantum mechanics must be incomplete.
How did they argue that?
They said, look, when we measure particle A and find it's up, we instantly know particle B is down. Since nothing could have traveled from A to B that fast, particle B must have already possessed the property of being down all along.
It had that property hidden somehow.
Yes, they argued that either quantum mechanics is incomplete, there are hidden variables determining these properties beforehand, realism, or the theory implies faster-than-light influences, non-locality. They strongly believed reality had to be both local and real. Therefore, quantum mechanics must be missing something.
So they preferred hidden variables to spooky action. Made sense intuitively.
It did. And for about 30 years, this was mainly a philosophical debate. Is the theory incomplete, or is reality truly non-local?
Until someone figured out how to actually test it.
John Stuart Bell, in 1964, a brilliant physicist from Northern Ireland, he devised a mathematical theorem, now called Bell's theorem.
And what did Bell's theorem show?
It showed that if reality were based on local hidden variables, Einstein's preferred picture, then the correlations between measurements on entangled particles could only reach a certain statistical limit. There's a maximum amount of correlation you can get just from pre-programmed properties carried by the particles.
Like if you set up pairs of gloves, one left and one right, in boxes. Finding a left glove tells you the other is right, but that was determined from the start.
A good analogy for local realism. Bell calculated specific mathematical inequalities. Bell's inequalities that any local realistic theory must obey. But crucially, he showed that standard quantum mechanics, with its non-local entanglement, predicted correlations stronger than this limit. It predicted violations of Bell's inequalities.
So it gave an actual experimental test. Measure the correlations and see if they obey the local realist limit or the quantum prediction.
Exactly. It turned the philosophical debate into a question for the lab.
And the results? when people like Elaine Aspect actually did the experiments in the 70s and 80s.
The results were crystal clear and have been confirmed countless times since with increasing precision. Experiments consistently violate Bell's inequalities exactly as quantum mechanics predicts.
Wow. So Einstein was wrong. Reality is non-local.
The experiments tell us that you cannot have both locality and realism. At least one of our core classical intuitions about the world has to go. Most physicists interpret this as meaning reality is fundamentally non-local. The spooky action is real. The connection between entangled particles transcends space.
But wait, if the influence is instantaneous, can we use this to send messages faster than light? Build an Ansible, like in science fiction?
The crucial caveat. No, you can't. And this saves causality and relativity from being completely broken.
Why not, if knowing A tells me about B instantly?
Because while the correlation is instant, the outcome of your measurement on particle A is completely random. You can't control whether you get up or down. You find out what A is, and that instantly tells you what B is. But you couldn't use that to send a predetermined message like, hello.
Because you can't force A to be up or down on command to encode the message.
Exactly. The randomness on your end prevents information transfer. Entanglement reveals a deep, non-local interconnectedness in the universe, but it doesn't provide a communication channel. Reality is weirder than classical physics allowed, but not quite weird enough to allow FTL texting.
Okay, so these four paradoxes, superposition and the cat, wave-particle duality, the measurement problem, entanglement, they really lay bare the fundamental conflict between quantum math and classical intuition.
They absolutely do. And they set the stage for the different ways physicists and philosophers have tried to make sense of all the interpretations.
Right, the interpretations. Because the core math works but doesn't explain the why or how of things like collapse, people have built these frameworks on top.
Exactly. They're attempts to provide a coherent story, a worldview that incorporates the strange quantum rules. And they all involve making some kind of trade-off, giving up some cherished classical notion.
Let's start with the default Copenhagen. We touched on it, but what's the stance?
Copenhagen basically says, accept the weirdness as fundamental. Particles don't have definite properties before measurement. Goodbye, realism for unmeasured properties. Measurement causes an instantaneous probabilistic collapse. Goodbye, determinism for outcomes. Hello, non-locality and collapse. Wave and particle natures are complementary aspects revealed by different experiments.
So it's pragmatic. It tells physicists how to use the theory.
Extremely pragmatic. It gives you the rules for calculating probabilities and predicting experimental results. That's why it's often summarized, maybe unfairly, as shut up and calculate.
But the downside?
It's metaphysically unsatisfying for many. It doesn't explain collapse. It draws this arbitrary line between the quantum system and the classical observer apparatus without saying why or where that line is. Why should a measuring device made of quantum atoms suddenly behave classically and force a collapse? It feels incomplete.
It works, but doesn't paint a full picture of reality.
It paints a picture of what we can know through measurement, rather than what is independent of measurement. It takes an instrumentalist view.
Okay, so if Copenhagen feels incomplete, what's a more radical approach? Many worlds.
The many worlds interpretation, or MWI, proposed by Hugh Everett III in the 1950s. This one is philosophically bold. It solves the measurement problem by simply denying that collapse ever happens.
No collapse. Then how do we get definite outcomes? Why does the cat end up either dead or alive when we look?
MWI says the entire universe, including the observer, is always described by the smoothly evolving wave function. When a measurement-like interaction occurs, say the Geiger counter interacting with a radioactive atom, the wave function doesn't collapse. Instead, the universe branches.
Branches. Into what?
Into parallel realities. In the cat scenario, the universe splits. In one branch, the atom decayed, the poison was released, the cat is dead, and there's a version of the observer who sees a dead cat. In the other branch, the atom didn't decay, the cat is alive, and there's a version of the observer who sees a live cat.
So every quantum event, every possibility encoded in the wave function actually happens, just in a different universe.
That's the core idea. All possible outcomes are realized in different branches of this vast multiverse. There's no randomness in the evolution itself. The universal wave function evolves deterministically. The apparent randomness we see is just our subjective experience of finding ourselves on one particular branch.
What's the appeal of that, apart from sounding like science fiction?
The appeal is mathematical elegance. It takes the Schrödinger equation absolutely seriously and applies it universally to everything, observers included. No special collapse postulate needed. It restores determinism at the level of the multiverse.
But the cost. I mean, an infinite number of parallel universes constantly splitting off, that seems incredibly extravagant. Where does all the stuff for these universes come from?
That's the main objection: ontological extravagance. Supporters argue it's actually simpler conceptually because you don't need the ill-defined collapse mechanism. They argue the stuff is just different configurations within the existing universal wave function. But yes, it asks you to accept the existence of countless unobservable worlds. And it struggles to fully explain why we only ever experience one definite outcome, the preferred basis problem.
Okay, so MWI saves the math by multiplying realities. What about trying to go back to something more classical? Hidden variables.
Right, the approach Einstein favored. Hidden variable theories, like the de Broglie-Bohm pilot wave theory, try to restore both realism and determinism.
How?
They propose the wave function isn't the whole story. There are additional hidden variables that describe the actual definite properties of particles, like their precise position, which exist whether we measure them or not.
So the particle always has a position, guided by the wave function.
In pilot wave theory, yes. The wave function acts like a guide, or a pilot wave, steering the particle along a definite deterministic trajectory. The apparent randomness of quantum mechanics just comes from our ignorance of the particle's initial hidden position. If you knew it precisely, you could predict the outcome exactly.
That sounds much more classical. Real properties, deterministic paths. Did it work? What's the catch?
The catch is Bell's theorem again. Bell proved that any hidden variable theory that reproduces the predictions of quantum mechanics must be non-local.
So to get realism and determinism back, you still have to accept spooky action at a distance.
You absolutely do. In the pilot wave theory, the guiding wave function instantly influences the particle's trajectory based on what's happening elsewhere, even far away. So you trade the Copenhagen measurement problem for explicit non-locality. You can't have local realism. Pick your poison.
No free lunch then. Okay, one more category, the role of consciousness.
This is probably the most controversial group of interpretations. They tackle the von Neumann chain, that infinite regressive measurement, head-on. They propose that the chain only terminates and the wave function only collapses when the information reaches a conscious mind. The idea is that consciousness is somehow fundamentally different from physical systems and has the unique ability to resolve the quantum superposition.
So a measurement isn't complete until a person actually becomes aware of the result.
That's the proposal, associated with figures like John von Neumann in some readings and Eugene Wigner. It seems to elevate consciousness to a special status in physics.
But what counts as consciousness? A cat, an ant, a thermostat. And what about the universe before conscious life evolved? Was it all just a giant superposition?
Exactly the problems. It's very hard to define consciousness scientifically, let alone give it special physical powers. And it clashes strongly with the standard view in neuroscience and biology that consciousness is an emergent property of complex physical systems, like brains, which themselves should obey quantum laws. Why would this emergent property suddenly gain the power to override the fundamental rules?
It feels like explaining a mystery with an even bigger mystery.
For most physicists, yes. It's not a widely accepted interpretation today, though it highlights the depth of the measurement problem and the seemingly special role of the observer.
So it seems no interpretation is perfect. They all force us to abandon some deeply held intuition about reality, locality, realism, determinism, or the passive observer.
That's the state of play. The math works beautifully, but the meaning is still intensely debated. But importantly, these strange features aren't just philosophical curiosities anymore.
Right, because now we're actually starting to use these paradoxes, aren't we? Building technologies based on superposition and entanglement.
Absolutely. This is the realm of quantum information science and quantum technologies. We're shifting from being puzzled by quantum effects to actively harnessing them.
Let's talk about the qubit first, the quantum version of a computer bit.
So a classical bit in your current computer is always either a 0 or a 1, simple binary state. A qubit, because it's a quantum system, can leverage superposition. It can be a 0, a 1, or crucially a blend of both 0 and 1 at the same time.
Both at once. How does that?
If you have multiple qubits, their potential states multiply exponentially. 2 qubits can represent 4 states simultaneously, 0, 0, 0, 1, 10, 11. 3 qubits can represent 8 states. With just, say, 300 qubits in perfect superposition.
Yes.
You could represent more states simultaneously than there are atoms in the known universe. This allows a quantum computer to explore a vast number of possibilities in parallel.
Which could lead to massive speedups for certain kinds of problems.
Exactly. Problems like factoring very large numbers, the basis of most current internet security. Peter Shor developed a quantum algorithm that could do this exponentially faster than any known classical algorithm, or simulating complex molecules for drug discovery or material science, which is incredibly hard for classical computers.
But building these quantum computers is hard, right? Because of that decoherence thing.
Extremely hard. Maintaining that delicate superposition and entanglement, which is also used to link qubits, requires incredible isolation from environmental noise vibrations, heat, stray magnetic fields. Decoherence is the enemy. It constantly tries to collapse the qubits back into classical zeros or ones, destroying the quantum computation. It's a massive engineering challenge.
Okay, so computing is one area. What about entanglement itself, that spooky action? How are we using that?
Two key areas are quantum communication and cryptography.
Quantum teleportation, that sounds like Star Trek, but it's real.
It is, but maybe not quite like Star Trek imagines. It doesn't teleport matter. It uses entanglement to transmit the exact quantum state of one particle to another distant particle.
How?
You create an entangled pair, send one particle B to the destination. You then perform a joint measurement on the particle you want to teleport, A, and your local entangled particle, C. This measurement destroys the state of A, but the result tells you exactly how to manipulate particle B at the destination to make it an identical clone of the original state of A. The information about the state transfer happens instantly via the entanglement correlation, though you still need to send the measurement result classically at light speed to complete the process.
Still amazing. And the unbreakable codes. Quantum cryptography.
This relies on a fundamental principle called the no-cloning theorem. Quantum mechanics forbids you from making a perfect copy of an unknown quantum state.
You can't just quantum photocopy it.
Nope. So if Alice sends Bob a message encoded in the quantum states of photons, like their polarization, any attempt by an eavesdropper, Eve, to intercept and measure those photons must disturb their state.
Because measurement collapses the wave function.
Precisely. That disturbance can be detected by Alice and Bob when they compare notes about a subset of the photons. If there's a discrepancy, they know someone was listening, and they discard the key. The security is guaranteed by the laws of physics, not just by mathematical difficulty like current codes. It's already being implemented commercially for secure communication.
So we're really weaponizing the weirdness.
Or harnessing it for good, but yes.
Yeah.
And it's not just physics labs and tech companies anymore. This weirdness might be happening inside us.
Quantum biology. That sounds almost contradictory. Biology is messy, warm, complex. Quantum mechanics seems to need cold, isolated systems.
That was the standard thinking for a long time. Decoherence should happen almost instantly in a biological environment. But increasingly, evidence suggests that some life processes might actually exploit quantum effects.
Like what? What's the poster child for this?
Photosynthesis, the process plants and some bacteria use to convert sunlight into energy.
How could quantum mechanics play a role there?
It's about efficiency. Photosynthesis is incredibly efficient at capturing light energy and transporting it to the reaction centers, where it's converted to chemical energy, almost on 100% efficiency in some cases.
That's impressive. How does quantum help?
When a photon hits a light-harvesting molecule, the energy, called an exciton, needs to find its way to the reaction center through a complex network of other molecules. Classically, you'd expect it to hop randomly, losing energy along the way.
Like finding your way through a maze blindfolded.
Right. But the evidence suggests the exciton doesn't just take one path. It seems to use quantum coherence superposition to explore all possible paths simultaneously.
Like the electron going through both slits. The energy tries all routes at once.
That's the idea. It performs a sort of quantum search, instantly finding the most efficient pathway to the reaction center before decoherence has time to set in. The biological structure seems perfectly tuned to protect this fleeting quantum coherence just long enough for it to be useful.
So life might have evolved to use quantum tricks for efficiency.
It looks that way. Other potential examples are being studied in bird navigation, using quantum entanglement in their eyes to sense magnetic fields, enzyme catalysis, quantum tunneling, helping reactions happen faster, and even our sense of smell. It's a young field, but really blurs that line between the quantum and classical worlds, suggesting quantum effects aren't just confined to the lab.
Wow. Okay, so from technology to life itself, these quantum paradoxes are everywhere. It really forces a philosophical reckoning, doesn't it?
It absolutely does. We have to rethink some very fundamental assumptions.
Like the idea of objective reality itself. Classical physics gave us a world that was just there, independent of us. Quantum mechanics seems to take that away.
It certainly makes it problematic. If properties aren't definite until measured, and measurement involves the observer, then the very notion of a pre-existing observer-independent reality is challenged. Maybe science isn't describing the world as it is, but rather the world as it appears through our interactions.
The line between the map and the territory gets very blurry.
Very blurry. The separation between subject and object, observer and observed, which was so central to classical science and philosophy, seems to dissolve at the fundamental level.
And what about causality? That neat chain of cause and effect.
Quantum randomness seems to break it. If an atom's decay is fundamentally probabilistic, not determined by any prior cause, unless you believe in hidden variables, which have their own issues, then strict determinism fails. The universe has an element of irreducible chance built in.
What does that mean for big ideas like free will? Does randomness open a door for freedom from physical determinism?
That's a deep philosophical debate. Some argue, yes, it breaks the causal chain, allowing for something non-determined. Others argue that replacing determinism with randomness doesn't give you meaningful agency or control, just randomness. It's not a simple equation like quantum randomness, free will, but it definitely complicates the deterministic picture.
And lastly, this idea of holism versus reductionism. Classically, we thought we could understand the whole by understanding its parts.
Reductionism, yes. Break everything down into fundamental particles and their interactions. But entanglement challenges that profoundly.
Because entangled particles remain connected no matter how far apart.
Exactly. They behave as a single, unified system, even across vast distances. Measuring one instantly affects the state description of the other. This suggests the universe might not be just a collection of separate parts. At a deep level, it might be fundamentally interconnected, holistic.
The idea that the world is made of separate, independent objects might just be an approximation that works well at our scale, but fails fundamentally.
That's a very real possibility suggested by quantum mechanics. The apparent separateness of things could be an illusion, emerging from a deeper, indivisible reality. It's a radical shift from the classical atomistic view.
So wrapping this up, quantum mechanics is this incredibly precise, technologically powerful theory
that simultaneously forces us to confront the limits of our intuition about reality, existence, causality, and connection. The tension between its practical success and its conceptual strangeness is still the driving force behind so much fundamental physics.
And for you listening, these abstract paradoxes we've talked about, superposition, entanglement, they're not just historical footnotes. They're literally the building blocks for future technologies. Quantum computing, secure communication. Understanding these concepts is becoming increasingly important.
It's moving from the physics journals into engineering and potentially into everyday life.
So we'll leave you with a final thought to chew on. If entanglement shows that reality at its deepest level is non-local and interconnected, with particles linked instantly across space,
how might reflecting on that fundamental holistic nature of the universe influence how we think about ourselves, about our own identity and our connection to others and the world around us in our everyday macroscopic lives?
Something to consider. Thanks for joining us on The Deep Dive.